So do y'all have any questions on any of these online quizzes? Again, if you can do the quiz questions when you're ready for the test. No questions? I figure what we'll do now is start reviewing. And I figure, so this is today, the 17th. This week, next week, I figure we'll do test 3 next Thursday. And we'll just review between now and then. I did want to say a little bit more about solubility and acid base. I don't know what I'm going to do about that, but for now, I think we should just start reviewing what I've gone over for test 3. So if we did test 3 on the 24th, that gives us this next week to review for the final. And really, we kind of have 2 weeks to review for the final, because our final isn't until Thursday of finals week. But we don't meet for class, but still, they give you time to go over things and meet with me if you need it, that type of thing.
Will the final be over normal class time?
I looked it up earlier, and I believe we meet on that Thursday, not at 9:30, but at 9 o'clock. And it's from 9 o'clock to 11 o'clock. I'll double check that, but I think that's correct. But I don't want to send y'all to 11:52 without saying anything more about solubility and acid base, but I just don't know what I'm going to do about that. I feel like we should just start reviewing for test 3 at this point. I'll figure out what to do about that. But for now, just focus on, so the quizzes that I put up already, those are what you should be looking at in preparation for the test next Thursday. And so, yeah, so I figure I'm just gonna review those topics. So we started, in some sense, actually, I went back to a little bit on polarity from chapter 4. Let me bring up the quizzes. In polarity, you need to have some grip on polarity to understand the intermolecular forces, because polarity creates dipoles, which is one of the intermolecular forces, dipole-dipole interactions. But I'll review that too. So there was polarity, electronegativity and bond polarity, polarity of molecules. I'll come back to that, but let's start reviewing at equilibrium. So in this chapter, kind of everything in these blue boxes give you all the logic you need to answer these questions. But I guess I will start with all right. So problem 6.7. Could you guys answer this question? Given these as the equilibrium constants, are products favored or reactants favored? For A, that's 10 to the negative 4. I'll write this on the board. The equilibrium constant brackets mean amount. Usually, it means concentration, but just the amount. So at equilibrium, this is the other thing to know. At equilibrium, these reversible reactions, you put them in a reaction vessel, you let them react, and they come to a point where there's some of this and some of this still in the reaction chamber. And it just sits there. That's what equilibrium means. So both of these exist. When there's more products than reactants, when this is large and this is small, you have a very large K. That is, if that equilibrium, while it's just sitting there, is shifted way towards products, you have a very high value of K. When there's very little products and mostly reactants, then you have a very, very, very low value of K. That is, this is very large and this is very small, and you get a little tiny fraction, which is when you have 10 to the negative something. So, based on that logic, this is the K value. 5.0 times 10 to the negative 4. Is this shifted towards reactants or products? If K equals 5 times 10 to the negative 4.
Reactants?
Yes. When it's very, very small, that means it exists, that reaction exists mostly as reactants, not products. You see that? And vice versa. Here's one that's very large, times 10 to the 5. So what is that? Products or reactants? What? Say again? Products, yes. Shifted towards products. What would you say about this one? It doesn't have a power of 10, but it's 350. Shifted towards products, but only a little bit shifted towards products. And this one's a fraction.
Yeah.
Shifted towards reactants. Shifted towards reactants. Because it's fraction, but only shifted toward reactants a little bit. Okay, consider the following reaction. They give you the reaction, they give you the K value. The actual expression that you would write for this one, because this is really sort of in quotes, because the more specific way to write this would be, so the reactants here is H2. This one, concentration of H2, usually in molarity. And this 2 that I put here, that 2, is this 2. There's a 1 here, and a 2 there, so 1 and 2. There's a 1 there, but we usually don't write those. So if you're actually going to calculate the equilibrium constant for this one, that's the way you do it. You find the concentration of these at equilibrium, and you can calculate the K value. That was A. B, are the reactants or products favored at equilibrium? Very high K value, 10 to the 7. So products are reactants. Yep. When products are favored, if I drew that energy diagram, when products are favored, usually it's like this when products are favored. Products are lower in energy than reactants. So is that delta H positive or negative? start out here and then you end up down lower. So this is delta H, negative. It's negative because energy came out. D, or reactants or products lower in energy. It's products. You couldn't predict the speed of this reaction because you would need to know the activation energy. Calculate the equilibrium constant. I'm trying to avoid just going through these questions. So you still have these as practice. But maybe I should go through some of these. Temperature increase, okay. We'll get to, so there's the Chatelet's principle that's based on increasing and decreasing the amounts of reactants or products. And then there's increasing or decreasing temperature and increasing or decreasing pressure. And then the effect that has on equilibrium. So I guess I'll just do this. I don't like the way this first one is phrased. But let me show you all this the way I taught it. Reactants. So there's exothermic and endothermic. Think about it like this. If it's exothermic, you do the reaction and you get some heat from the reaction. Heat comes out of the molecules. If you think like that, it's like heat is a product of the reaction. So I would write heat here. This is exothermic reaction. So I told y'all to put heat on the right side if it's exothermic. And now you could ask that question. If you increase temperature, it's like increasing this. Which way does it shift if you increase heat? Endothermic, I told you to do the opposite. It's like heat is a reactant that needs to be added. So this is that's when you're dealing with temperature. So if it's an exothermic reaction, concentration. Okay. I have a reaction, it's in the reaction vessel. And then I take that reaction vessel and I increase the amount of products that's there. This is Le Chatelet's principle. I increase the amount of product that's there. Which way does it shift? Left or right? Anybody else? I increase the amount of product, it shifts to the left. I decrease the amount of product, it shifts towards the product. Shifts right. If If I increase the amount of reactant, it will shift to the right. If I decrease the amount of reactant, it will shift towards the reactant, that means to the left. If you can remember that, the rest of this just flows from there. So this is, Le Chatelier's principle. That thing about increasing, decreasing concentrations, which way will the equilibrium shift? But that same thing works up here for endothermic and exothermic, if you can follow my convention of putting heat where I tell you to put it. If it's endothermic, you put heat here. If it's exothermic, you write heat here, and then you can do the same concept. Increasing heat for an endothermic reaction shifts equilibrium to the right. Decreasing heat for endothermic will make it shift to the left. Increasing heat, shift to the right. Decreasing heat, shift to the left. See what I'm saying? And if it's an exothermic reaction, increasing heat shifts to the left, decreasing heat shifts to the right. A reaction, so in favoring, the word favors means shift towards that direction. I just don't like the way that's phrased. Temperature is increased, a reaction that blanks heat is favored. That favored means shifts to the right. That's my problem with that question, is the way it's phrased. Let me just go past that one. Okay, the third thing, there's three of these to understand. The third one is about pressure. And this is about gases specifically. So for this one, let me write this equation here. SO2, so it's this one. 2 SO2 plus O2. And I'm missing something important that I haven't written here, and that's these in parentheses. The G means it's a gas, and that's important for this one about pressure. So you need to look at that. But that's why I wrote gas here. This specifically refers to reactions where the constituents are gaseous state. But what you're looking at is, I'm going to use the moles as my unit here, but how many moles of gas are on this side? 3. There's 2 of these and 1 of this, so there are 3 moles of gas on the left side. And how many moles of gas are on the right side?
2.
So for this, I would write it like this. You put the P on the side that has the more gas. So in this case, I would put C2 gas. So for this example, because there's more moles on the left side, I put the P here. Now, increased pressure, you shift to the right. Decreased pressure, you shift to the left. Same pantomime I was doing here. Increase the reactant, goes that way. Decrease the reactant, comes this way. Increase pressure, you shift that way. It's basically just trying to shift the gas into a smaller space. You decrease the amount of gas as you increase the pressure, and vice versa. If you release the pressure, it wants to expand this way. How is this one phrased? So if you're going to favor the formation of products, that would be shifting to the right. That would be increase. Equilibrium favors the blank when the equilibrium constant is much greater than 1. Reactants are products. That's really what's missing from these questions, is to tell you what are the choices of the answers. So the answer here is either reactants or products. Which is it? Because if K is much greater than 1, it favors the products. That's right. Okay, increase the concentration of C2H6. So your first thought is, does that shift to the right or shift to the left? This one doesn't have the double arrow, so this one's really a question about reaction rates. But increasing the amount of a reactant increases the reaction rate because it increases the frequency of collisions. So this one's slightly off topic from what I did here, but see that there's a single arrow here. So increasing the reaction, increasing the concentration of C2H6 increases the reaction rate of this, but I'm not sure why I put that in here. Oh, this section is reaction rates and equilibrium. So I'm sitting here talking to you about equilibrium, but that one's just on reaction rate. Do you remember what changes the activation energy? There's only one way to change the activation energy, to decrease the activation energy. Putting in a catalyst is the only way to change the activation energy. Next question. Catalyst accelerate a reaction by is lowering the energy of activation. Activation energy. I was talking about equilibrium, but now I'm shifting a little bit. So there's an example of a reaction. This is progress of the reaction. This is energy. This is the delta H. This delta H is positive because this has gone up. But what I really want to show you is that. That's the activation energy. It's like a barrier that the reaction has to overcome And if you so this level is the same as this level. This level is the same as this level. It's the same reaction, but this reaction used a catalyst. It decreased the activation energy. This reaction will go faster than this one because the activation energy has been lowered. You guys get that? So this has a catalyst. Where was the activation energy? What was the question? Oh. So EA is a symbol we use for activation energy. So which one of those is going to have the fastest reaction? That will be the fastest reaction. And this next one says which one will be slowest? The one with the highest activation energy will be the slowest. An equilibrium constant that's really large, 10 to the 6, indicates that at equilibrium, what's the answer here? Products are favored. We ought to read the rest of this. That's the only correct answer. Equilibrium constant that's very small, 10 to the negative 9. What does that mean? Reactants are favored. Which one of these are products favored? K equals 1 means there's equal amount of products and reactants. 10 to the 4 is going to be the answer to this question. K equals 10 slightly favors the products, but only very slightly. So this probably isn't phrased very well, but this one by far will favor the products. And which one when the reactants are favored? The third one. The one that's got a very small K value. When the pressure of a gas phase reaction at equilibrium decreases, which direction does the equilibrium shift? So what's the answer here? It's either the first one or the second one. Which one is it? Decrease the pressure. It's the first one. Oh yeah, point of the board again. That's this. So decrease the amount of pressure you're going to shift towards whichever side has deviation like this. More moles of gas were on this side, so that's why I put the P here. So one like this. So whichever situation you're in, increasing the pressure shifts towards less moles of gas. Decreasing the pressure shifts towards the side that has the more moles of gas. You guys get this? Endothermic reaction at equilibrium, increasing the temperature does what? It's up here, talking about temperature. It shifts the equilibrium constant endothermic. So we're talking about this. And remember, K is increasing the temperature. It says endothermic reaction, increasing the temperature. So we're here, we increase the temperature. If we're gonna shift this way, that is, we're gonna increase this and decrease this by increasing the temperature, what is that gonna do to K? Increase that and decrease that. Yep, K will increase. So it increases the rate of the forward reaction. All the phrasing of these different questions. Increase the rate of reverse reaction. Yeah, to form more products. Yeah. So the four things, so we're back to rate of reaction, not even really talking about equilibrium for number 15. Do you know the answer to this one? What? Yeah, it's all of them. Increasing the temperature makes them move faster, so they bang into each other more often. So the collision rate increases when you increase the temperature. Increasing the concentration of a reactant increases the amount of collisions because there's just more of them there, so there's more of them bumping into each other. Adding a catalyst, that increases the reaction rate because it decreases the activation energy. And I'm not sure I mentioned this, but they do have to be in just the right orientation to react. You've got two reactants, they need to find each other and bump into each other. B, they need to be in the right orientation to make the reaction happen. So you can get two reactants that bump into each other but don't react because they weren't in the exact right orientation when they bumped into each other. So the orientation matters too. So yeah, those are the four things that affect reaction rate. Did I answer all these? I skipped a couple of them. So you should go through these and make sure you understand them. Just didn't answer some of these. Okay, equilibrium and reaction rates. The gas. I really didn't do the gas laws the same way the book does. I just never liked how books do these. So I kind of boiled 7.3, 7.4 together into 7.5. Remember how to do these? Have you done these? Okay. So these types of questions. These gas law questions, you always start with And there's two different variations of questions you'll get based on the gas laws. One of them, things are changing. There's an initial state and a final state. And then some of the questions you'll get just gives you 3 out of 4 of these variables. This is a constant, depending on the units you're using. You'll use one or the other constant. But you'll be given 3 out of 4 of these variables, and you just solve for the 4th. So either you've got a situation where you've got a beginning state and an ending state and something changes, or you've got a question where nothing's changing, you're just given 3 out of 4 variables and you solve for it. This first one, notice it says, what is the pressure exerted by the gas if the volume is increased? Well, that tells you something changed. So this is going to be one of those problems where something's changing. When something's changing, go ahead, just to stay organized, pressure, volume, number of moles, temperature. Go ahead and just write this down. And usually not all of these things are changing. Okay, this says a sample of neon gas has a volume of 5 milliliters at this pressure. What is the new pressure when the volume is increased? It mentions temperature. It says, the very last thing it says is at constant temperature. So these are constant. But it's also typical for these problems to just not mention it. Notice the number of moles wasn't mentioned. This wasn't mentioned. So if it's you're either told explicitly that this doesn't change, or it just doesn't mention that at all. Moles weren't mentioned at all. And they just happen to throw in the temperature is constant, but even if they didn't put those last 3 words there, the only place temperature is mentioned is here. They could have left that off and you would just assume that that's constant because it wasn't mentioned. So what's changing here is pressure and volume. In the initial volume, 5.0 milliliters, and 1. We're told the next volume is. So we're given that, and this is what we're trying to find, pressure. So if you'll set up the problem like that, then you can do this. Next, you're gonna go, so this is the standard way to write this formula. And what I would say is, this isn't the best example to start with, but what I would say is, you use algebra and you just do what you need to do to put the things that are changing on the left and the things that are not changing on the right. It just so happens it's already there. The PV equals nRT, so I don't have to do any algebra, so it's not the best example. But it's pressure and volume. Pressure and volume are already on the left, and all the things that stay constant are on the right. So then you go, and now you can solve it. You just plug in your values and solve it. Go to the next one. Another thing to remember when you're using PV equals nRT is you always have to put your temperature value in Kelvin rather than degrees C. But so this next one is another things are changing type problem. All right, so what do we have? Balloon is at this volume of liters, helium 25 degrees C. But I have to turn that into Kelvin, and cooled to 11 degrees C. But I still have to turn that into Kelvin. And they went to the trouble to say constant pressure, but they didn't have to. They could have just not mentioned it. And of course, moles are not mentioned. And what we're being asked for is the new volume. What volume does the balloon now occupy? You see how I set this up? So if you can get all of this, the rest is PV equals nRT. The things that are changing are the volume and the temperature. So I need volume and temperature on the left, and I got to get pressure over to the right. With a little bit of algebra, I'll have this. Divide both sides by T, divide both sides by pressure, you'll have that. And then this is what you're using. You could solve that way. But don't forget, these need to be in Kelvin. The way to put these in Kelvin. Add 273.15. It's 298. So those are the actual values that you need to use for T1 and T2. So there you have 3 out of 4 of these variables that solve for the fourth. Sounds familiar, right? One of these, Chewy, which one of these did I say was phrased badly when we talked the other day?
I think it was, maybe number 5. Yes. No, it's
We went over almost all of these, so I don't remember which one.
maybe number 7. Was it number 7?
Oh, yeah. Standard temperature and pressure. Don't worry about that for the test, but you wouldn't be able to solve that one if you didn't know that standard temperature, it's usually abbreviated STP, standard temperature and pressure. Standard temperature is 20 degrees C, but if you add the 273, you end up with 293, so 293.15. And then standard pressure is 1 atmosphere. So to solve that problem, you would have to know that, and I don't think I said that out loud. But standard temperature is 20 degrees C, standard pressure is 1 atmosphere is what we're experiencing right now, or something very close to it. But I'll go ahead and solve this one, because now number of moles is changing. Or no, number of moles is not changing. Number of moles is not changing. In fact, nothing's changing. Read that problem and pay attention with your own brain to interpret, is anything changing in that problem? See what I'm saying? Nothing's changing in this problem. You're just flat using that equation the way it is without doing a little algebra, deciding what's changing and what's not. And what you're using is, for pressure, it's 1 atmospheres. For temperature, it's 298.15 is a standard temperature and pressure. They give us 5.33 liters for volume, and it's asking us how many moles. This is a constant, and I'll give you this on the test. There's two values. Figure out where it is in here. R values. I said this in class the other day too. I'm happy to give you this on a test if I give you a question, but pressure shows up and there's just a ridiculous number of units for pressure. Atmospheres, millimeters of mercury, torr, pounds per square inch, and this is called the Pascal. But I didn't say much about those. Where are the R values? Again, I will give you these on a test. I sometimes have them memorized and I forget them sometimes. Good Lord. It's here somewhere. We found it yesterday, Juhi. Where is it?
Which one are we talking about?
I'm looking for the R values.
Or PSI,
Was it up there?
there was one question that has a PSI, and I didn't figure it out, so we have to like look up which one is.
It's gotta be at the beginning. It's not gonna be in the first section.
And I remember there was only for ATM and MMHG in the textbook.
Yeah, there's only those two values. They're given somewhere. I have them saved in my phone.
Are we given standard temperature like on?
I don't mind telling you what standard temperature and pressure is. Don't get hung up on memorizing things. There it is. So your book will tell you two different values for R. One of them is 0.0.
Okay.
21. And the units on here. Okay, that's one of the R values, and the other one is just doing millimeters of mercury instead. And that one is. I bet your book says 62.4. So different units for the pressure, that's all that's different here. And we were given pressure in atmospheres, so we're going to use this one. But you see now we have 4 out of 5 variables, and we just solve for n. And I will give you those on the test here. I don't make y'all memorize. So that's how you'd solve this one. Yesterday I calculated this, and I think I got 22.2 or something. For some reason it was off. That was the other problem with this one. So let me solve it. Go through solving this. Ultimately, you're going 1 atmosphere 5.33 liters, and then I'm gonna divide by 298.15 K. And then uh, 5.33 divided by 298.15. Yeah, I get, we're gonna assume the one atmosphere is infinite, so it's exact. That's what it was this being exact that bothered me yesterday. But I come up with n equals 0.22, my calculator says 2. But I'm only gonna keep 3 significant figures for these. That really has infinite number of significant figures. So I would keep this, so I would have 0.218. And that's not in the, that's not among the answers. But use that as your guide for this question, because 218, it's probably this one they were shooting for, but I don't know how they got 238 there. This one, so they're giving you one of those 3422. That one, they're just giving you one of those more exotic pressure units. I better solve this though to see what answer they have. 3422. So if you got this question on a test, I would give you the conversion factor you need, which is here. So all of these, the 14.7 PSI, equals 1 atmosphere. So that's what everything in that box is telling you what it is in 1 atmosphere. 1 atmosphere equals 1 atmosphere. 760 millimeters mercury equals 1 atmosphere. 760 torr equals 1 atmosphere. 14.7 PSI equals 1 atmosphere. So you would have to take this and turn it into atmospheres. And then you would be able to solve this one. But let me go through the solution, double check the answers. 3422 divided by 14.7. 3 significant figures, 4. Well, I guess we'll stick with 3 here. 233 atmospheres. And again, read this one to convince yourself that nothing is changing. Read this question and recognize that nothing's changing here. So we're just going to use that formula to solve. 25 degrees C, 25, this has nothing after the decimal, so I'm not going to keep any of that. So 397 is what I've got. So So I've got my pressure and I've got my temperature, and now it's just a matter of solving. Um, I need to solve for N, so it's PV over RT N. Pressure is 233 atmospheres. Volume is 12.6 liters. That's the R value, and the temperature was that'll give me moles. You guys follow this? I'm kind of stumbling my way through it, but 233 times 12.6 0821 divided by 397. I get get 90 point something.
Should the temperature, shouldn't it be 297?
Yes. That was a 2. No. No, it should be 3. It's 273. Good Lord. I knew I was stumbling somewhere. 273.15. So 298. Yes, I made a mistake on temperature. 273.15. Oh, 821. 198. Okay. So now I've got 119. Keeping 3 significant figures, I guess, so 120. Yes. 120, and yes, with a decimal. You guys follow that? These PV equals nRT things are it's just a little exercise in algebra if you can peel the information out of the question. This one. One atmosphere. Okay. This one just seems tricky because it's got a equation here. It shows you the reaction, but you don't need that reaction to solve this. Moles. I probably won't ask you one like this on the test. I won't ask you one like this on the test. But you would have to figure out how many moles of gas is here, of O2, and then solve it, but don't worry about that one. So I won't go through the solution, but pretty sure the rest of those questions are good for the test, but let me look again. Yeah, so don't worry about 9, but you would use the amount of H2O2 to predict how many moles of O2, and then that would be your moles. And then the rest you're given and you can solve, but don't worry about number 9. What else can I review? Intermolecular forces. There is one other thing to mention that I haven't mentioned yet, intermolecular forces. What I did tell you is the weakest intermolecular force. Do you remember what the weakest one is?
London dispersion forces.
Yep. I just call these LD forces. That's London dispersion, sometimes just called London forces, sometimes just called dispersion forces. That's the weakest. Do you remember what was next? Dipoles are what you get when you have a polar molecule. So this is based on polarity. So you have one molecule and you have another molecule and it has that pole. The dipole is a slightly negative charge and a slightly positive charge. Slightly negative charge on one molecule. This is the bond. And on another molecule, you have another slightly positive, slightly negative, and these are attracted to each other. So dipole-dipole interaction is what that is. Hydrogen bonding is dipoles. It's just very extreme dipoles, and there's only 3 in existence in the universe. It's a bond between H to F, H to O, and H to N. That's it. So if it has a F to H bond, it's a molecule that has an H to F bond. If it's a molecule that has H to O bond, or if it's a molecule that has H to N bond, it has these extreme dipoles. We call that an H bond. And these are way stronger than these. So weakest, kind of in the middle, way stronger than these. But there's a couple other I haven't mentioned. So dipoles are partial charges. If you have, the next one on this list would be ion dipole. So let's say you had Na plus floating around in some water or something, and then you also had a dipole. That attraction is stronger than that attraction, and it's even stronger than these, because this is a full charge. So that has a really strong attraction to this negative charge. And it could also be negative ions. But an ion being attracted to a dipole is stronger than these. And then the strongest one is ion to ion. Now, both things are a full charge, and that's an even stronger attraction. So I don't think I mentioned these. And these are called that's called an electrostatic interaction when it's a full charge. I don't think I said that. So you wouldn't have been able to answer this first one. But this is the order they go in. Do you see why that's the right answer to this one? Strongest one is the electrostatic interaction. The only one not mentioned in those 4 is the ion dipole. But you see the logic. I will give you a structure to look at for the test. There's a couple of these where they throw them at you as a formula. I think you could figure these out, but I'll go ahead and give you the structure so you can see into it. But here they give you the formula and they give you the structure. So what is the strongest type of intermolecular force that this molecule has? Yeah, I think you can see it even without calculating polarity. Hydrogen bond. It's got an O to H bond. That's all there is to it. That's the strongest one. There's no ions, so it's not going to be ion-ion or ion dipole. But you see the O to H bond? That means this has hydrogen bonding, so it's very strong attraction. How about this one? What's the strongest molecular force here? There's no ions, so it's not the first two. Does it have O to H or N to H or F to H bonds? So it doesn't even have that. And I'll go ahead and tell you that there's no polarity there either. C to C bonds and C to H bonds are not polar, so there's no polarity at all for this molecule. So what's the strongest? London dispersion forces. It's the only intermolecular force this has. Boiling points and melting points. The stronger interactions it has, the higher boiling point or the higher melting point you're going to have. So one thing you would need to know is where is the polarity. You see that this has O to H bonds. This one does not have any O to H bonds or H to F or N to H. So these two, you would have to know that O to C is polar. So these two molecules have some polarity. This molecule has no polarity. And this one definitely has some polarity. It has extreme polarity. So which of these is going to have the lowest boiling point? The weakest interactions. The first one. The first one only has London dispersion forces. This one has those hydrogen bondings, so these are attracted to themselves a lot more. So it's going to have the higher boiling point. And these will be in the middle somewhere. These have polarity, but not extreme polarity that you get with hydrogen bonding. And this is just the converse. Which one of these will have the highest boiling point? Which one of those has the strongest interactions? Huh?
Is the second one?
Second one. The second one has those hydrogen bonds. So this has polarity. So if you're going to order these in terms of boiling point, the highest boiling point will be this one because of those strong interactions, the hydrogen bonding. The weakest will be this one because it only has LD forces. All of these have LD forces, but this one has hydrogen bonding. And these two would be in the middle somewhere. Exactly which one is higher or lower. I think this one would probably be higher because it's a lighter molecule, but I'll go into that detail in 1152. This is hard to see into, but like I said, I would give you the structure of these. But CCl4 is the one here that's completely non-polar. There's no polarity in CCl4, which is why that one's going to have the weakest. Yeah, so this only has London dispersion forces. Maybe I should. So O to H, N to H, the only other one is F to H. To answer this one. I should probably give you guys